Well, thanks to the organizers. I've really enjoyed the program. This has been an excellent workshop with a lot of variety, and so I'm going to make things even more varied by telling you about some active matter avalanches. So I'm going to talk to you about jamming and clogging in both granular and active systems. Let me first acknowledge my collaborators. So I work extensively with Charles Reichhardt at Los Alamos, and some of this work has been done with Andras Liebal, who is a professor at Babis Bolyai University, and his student, Huba Peter. Oh, do I need... Is that, can you hear me in the very back? Okay, they're good. All right, so very brief outline. I'm going to first show you the distinction between jamming and clogging in a granular system. Then I'm going to define for you what is active matter, and a bit why it's interesting, and show you how you can also get jamming and clogging in active matter. And then at the end, I'll show you, as far as we know, the first measurement of active matter avalanches. So this conference, we've already seen granular systems, so I'll give a very brief introduction. For me, the key element of a granular system is that these are particles that have no tensile component to their interaction. So they have no attraction. They'll just, they can push against each other, but they can't hold together unless they're confined in some way. But if they are confined, they can act like a solid. And so this has already been shown, this jamming phase diagram idea from about 20 years ago, that as a function of temperature, load, or inverse density, as you compress your granular packing, you can make a transition at this point J from a regime where it's able to flow easily to a regime where the system acts like a solid. Now this transition has been suggested to be of a second order nature, even though this is an athermal system. And so if that's true, you would expect to see some kind of diverging length scale at this transition. So quite some time ago, we did a measurement of this diverging length scale by realizing this little thought experiment that had been proposed in the O'Hearn et al. Paper, that you have a packing of disks, you make it denser and denser, and if you try to push one of the disks, how many other disks do you have to push out of the way in order to get it to move? So we did a very straightforward simulation, two-dimensional. We ignore inertia here, so we just have disks of two different sizes so that they won't crystallize, a radius ratio of 1.4 to 1, which is what everybody uses. The disks have an extremely stiff spring because we're doing molecular dynamics. We can't do true hard sphere interactions. They don't know about each other, and then when they're touching, they push each other firmly away. And then we're going to drive one of the disks as we make the remainder of the disks more dense. So these are just some movies of this older work. So here there's periodic boundary conditions. This side of the system is attached to this side of the system. And what we're doing is we're going to grab this blue disk and try to push it through this packing of these background of black disks that are at some density. And then since it's well defined in the simulation, we'll color with red any disk that is in a force contact with a disk that's in a force contact with the driven disk. And so we want to see how many other disks do we push out of the way as we move this through. So if I can play this movie, there we go. So this is at a density below jamming, 0.801. So you can see the disk is making its way through the packing. You notice a few things. First, there is kind of a well-defined length scale here ahead of the moving disk. So it's needing to compress the packing about out to this distance in order to make forward progress. The other thing you notice is it's left behind a trail here. And this is because in the absence of any kind of long-range interaction, there is no energy cost to having a void in this granular system. It doesn't care. The density can be uniform or non-uniform. It doesn't make any difference to it. So there's no motivation for these grains to come in and fill this in. Yeah, so here we're just putting a constant force, and everything's overdamped. And we can measure the velocity of this disk, and this actually tells us how many other disks we're pushing as a function of the density. So now we can make things more dense, and this is essentially at the jamming transition within the resolution of our simulation. And so now what you see is as you try to push this, the disturbance immediately is propagating all the way through the packing, and it's reaching the limit of our finite size because it's touching itself. You'll also notice this disc is having a lot of trouble getting through the packing. It's no longer leaving a trail because the only way for it to make forward progress is it has to find enough discs that can kind of rotate out of the way, and so that some disc has to fill in behind it. And so of course eventually it's unable to do that. It reaches a point where there just isn't a rotation that can occur, and then it will stop moving. So here the simulation is still running, but the disk has ceased to make forward progress, apparently. In actuality, this disk is now pushing absolutely all of the other disks. So the velocity has become extremely slow, and the whole system has now become a solid. So by grabbing one part of it, we can push everything. We can measure the number of other disks that are being pushed, and from that extract a length scale. So this is as a function of the density of the other disks, and we find a divergence of this length scale, which goes as a power law as you approach this jamming point. This was one of the early measurements of the power law. We came up with a power that was between 0.6 and 0.7. There have been, this was back in 2005, there's been a lot of other work by other groups that I don't do any justice to in this slide that have verified and have made corrections to this scaling. But all of these see that indeed jamming does appear to have this second order phase transition type of signature with this diverging length scale as you approach the jamming transition. Now, what got us interested is this idea that if there's really a diverging length scale, I can think about having an obstacle instead of a driven grain. So if I change my reference frame, I can think about putting a post and trying to flow all my grains past it instead of pulling one grain through. And that's actually exactly the same in my simulation. I just changed how I'm interpreting my result. But if you think about it that way, then I can say, well, what if I put multiple posts down? When the average spacing between those posts is the same as this diverging length scale, you would think that I should be able to jam the packing early. So I should be able to depress the jamming transition in a way that depends on this diverging length scale. So we decided to set up this simulation. Here are the red disks. We've just taken them and nailed them down. So they're not able to move at all. And then we put a drift force on all the remaining disks to see whether they can flow past or not. So if we're in our jam state, we'll get no velocity, and if we are not jammed, we'll be able to see motion through. So here the black lines are these little where the disks have moved. So we see, if we look at the velocity as a function of the density of the grains, depending on how many of these posts we put down. If we have very few posts, we see what we'd already seen, which is the velocity is essentially free flow until we get very close to the jamming density, and then it plummets to 0. As you increase the number of posts here that's going this way, well, it's a bit harder to move initially, but the point at which the velocity plummets to 0 is indeed decreasing as we increase the number of posts. So this is what we were thinking. Yes, as there's this diverging length scale, we should be able to, as we add more posts and the distance between them gets smaller, we should be able to push this transition down. Yes? So that's, for this radius ratio of disks in 2 dimensions, the jamming density is at pretty close to 0.84. So this is well known. Well, for this particular radius ratio, if you had all monodisperse disks, it would be 0.9, except then it would crystallize. So we want to avoid that. But this is sort of the standard. Everybody does this radius ratio. Yes? This is all overdamped. However, we don't have friction on the edge of the grains, so the grains have no rotational degree of freedom. We want to stay simple. So as I was saying, we should be able to depress this jamming density as we add obstacles, and indeed that's what we find for low density of obstacles. But eventually, as we keep adding obstacles, we see something we didn't expect, which is that this curve turns over. And so once we have, in this case, about 10% of the disks are pinned down, we can always get the system to stop flowing, even as we drop the disk density well below jamming. So this is a density of 0.675. This is way below jamming. You wouldn't think I could get things to stop flowing down here. So this suggested to us, well, maybe there's a difference between what's happening up here and what's happening down here. So let's take a look at the behavior here close to the jamming point. What we find is here's our pinned disks. We set up the system, we start pushing the grains, and immediately it doesn't move. So we get an instantaneous jamming, and we get also homogeneous configuration. You can't tell in which direction I pushed this system. In fact, it doesn't matter. It's jammed in all directions. And there's essentially no plastic rearrangements. Now we can contrast that to what happens here. First of all, we find this really long time scale where the system starts flowing initially, but then the flow decreases, but it's still flowing and gradually decreasing. Then it starts to get rather intermittent. It thinks about not flowing, changes its mind, and then finally at some point it stops flowing. Since we have no temperature, once the system has stopped flowing, it can't ever start again. So this has made a permanent transition to not flowing. This is at a density of only 0.675, so very low compared to the jamming density. And here you can see I've already called this a clogged state rather than a jammed state. So why is that? Well, first of all, as we change the amount of disorder, this amount of time that it takes to reach this clogged state changes. So for low amounts of disorder, it's a very long amount of time, and then as you increase the amount of disorder, this gets shorter. So what the system is actually doing is, in some sense, it's cheating. We started out with a uniform distribution of disks, some of them nailed down. As time progresses, the disks start to flow. You start to see these areas where the disks have piled up, and essentially like a hopper-type clogging, except it's like we have a whole bunch of hoppers that are all coupled together. So we're still able to get some flow on the edges of the system, but over time there's rare events where the disks come to one of these bottlenecks at just the wrong arrangement, and they block up this bottleneck, and then they're no longer able to flow. So what the system has done is, even though we're at a density of 0.675, if you look at the locations of the grains, we have some areas where the density is at the jamming density, and other areas where it's empty. Because as I said, these empty regions don't cost any energy, so the system is fine with that. Yes? So what are you asking the red, the disorder, or? So we did, I don't show here, but I can show you afterwards, we did periodic arrangement. There you get irritations of, it matters which direction you drive, you can get locking of the direction, but actually we can get size-dependent sorting, so I can show you that afterwards. Yeah, so if you look closely, you get, these are all sort of like little tiny hoppers, where they've made the little, they've come and they've made a barrier, and then the other grains aren't able to get past. Well, it's frictionless, but it's overdamped. So it's frictionless. Yeah, so it's frictionless in the sense that there's no rotational degree of freedom of any of our grains. But the whole system is overdamped because we don't want to worry about inertia. So it's as if they're sliding on a surface that takes away their momentum. Okay, so let me go to, we did a more thorough study looking at the velocity of the system as a function of the density of the grains. And so we see these two regimes, the flowing regime and clogged. At high disk densities close to jamming, we get this behavior I showed you before, which is kind of dominated by this jamming transition where we're linearly decreasing our jamming density as a function of the number of obstacles. Then we have this very large plateau where for almost constant obstacle density we can make this transition from the flowing to the clogged state. And this is extremely robust behavior. So you can see this is going from around densities of around 0.7 all the way down to densities of 10%. At very low densities we actually get a different behavior because we're in the individual grain limit, no longer collective. We can look at the time required to reach this steady state. And so if we look at the velocity signature as a function of time, we can fit this to a stretched exponential and extract a time scale. What we find is that when we're in the clogged, when we're crossing the flowing to clogged transition, this time scale is very long. And in fact, it diverges right at that line separating flowing to clog with an exponent that we can extract of about 1.3. If we're going from the flowing to the jammed state at higher densities, then the time scale is extremely short. You really can't see it on this plot, but here you can see that the characteristic time is easily an order of magnitude shorter, and the exponent is quite different. Well, it's hard to get an exponent. There's not much of a divergence here, but it's quite distinct. And so if you look at that time scale, what you see is that you have very short times associated with the flowing to jam transition, and these extremely long time scales associated with the flowing to clog transition. Yes, oh yeah, I didn't write it on here. This is obstacle density, and this is the density of the particles. Sorry about that. So this diverging timescale that we see, the exponent that we find is actually the same exponent that is associated with an absorbing phase transition. A common example of that is a directed percolation transition. So some people in the audience may be familiar with this type of transition. Certainly it's well known in, say, if you're trying to extract oil from the ground. The question is, what is the probability of going from one, of being able to go from one point to the next point when there is a direction? So in other words, if I have fluid at the top of some rock, if my probability of having a pore is high enough, I can always get from the top of this rock to the bottom. As I drop that probability, I might be able to get some distance, but once I reach a point where there's no path, it doesn't matter how many paths there are down here in the bottom. Once I can't get past, that's the end. So this is a non-equilibrium transition, because I can go from the fluctuating state to the non-fluctuating state, but once I've reached the non-fluctuating state, I can't go back. So it breaks the symmetry of going across the transition. And then of course, right at the directed percolation transition, you have these extremely long time scales and also divergences in the length scales. Just as kind of an aside, we showed earlier, about 10 years ago, that there's a connection between this directed percolation type of transition and plastic depinning. I know some people have talked about elastic depinning transitions, but it's interesting to note that you can get these extremely long timescales if you have a system that's very close to sliding in a disordered way. Just a final note about the clogged state, it is fragile in the sense that it has information in it about which direction it was formed. So if I start flowing my system in the x direction and it clogs, if I rotate the drive by 90 degrees, it may not clog. It might continue to flow. So I can actually unclog it just by changing the direction. In this case, it formed a void when I was flowing the grains in the x direction, and then when I rotate the drive into the y direction, the grains are able to get into that void and keep flowing, and then there's not enough density here in this channel for this to ever clog, at least on the timescales that I measured. So that's a distinction between these two states. So just to summarize the whole distinction between jamming and clogging, we have the jamming transition up here at these high densities close to this original clean point J, but we have a big window of a clogging transition down at these lower densities. And so the jamming, it's a homogeneous process. It's jammed in all directions, and it appears to be associated with an equilibrium type critical point behavior where we have this diverging length scale. But in distinction, this clogging transition, it's extremely heterogeneous when you form the clogged state. It has a long transient time, and so it's associated with a diverging time scale. That makes it look similar to a non-equilibrium phase transition, or in this case, an absorbing phase transition. So our idea is that these clogging and jamming transitions are actually quite distinct. They're fundamentally different for the two types of systems. Now, in my remaining time, I want to get to active avalanches. So first I'm going to tell you about what is active matter, and then I'm going to show you how we can get active clogging and jamming as well. So what is an active matter system? Essentially, the idea is that it's some kind of non-equilibrium particle-based system where the particles have an internal source of energy so that they can move independently of any external fields. And so, of course, they're very common in biological contexts. You could think about birds or bacteria or fish, or you can have artificial ones like little robots. So these are able to run around under their own power. The thing that got us started in it was the idea of bacteria, which can undergo a run and tumble dynamics. This is E. coli. Essentially, the E. coli puts all its flagella on one side of its body and runs for a certain amount of time in some direction. And then after different conditions are met, it flails its flagella out. This is the tumble state, and then it rebundles them and picks a new random direction and runs. And by adjusting the length of time that it runs in one direction before tumbling, it can undergo things like chemotaxis. It can tell, like, well, there's not food here, there is food here. It can actually run longer when there's no food and then run shorter when there's food and get itself to stay in the area where there's food. This doesn't violate the second law of thermodynamics because this is a non-equilibrium system. This is a very key point about active matter. Now, a lot of advance has been made in active matter recently due to the creation of artificial active matter, because bacteria is really annoying. It knows how to do all these other things, like, collective waves and stuff. It's been around for a long time. So artificial active matter is really dumb. It just swims. And so you can use, for example, colloidal particles. These are basically plastic balls. In this case, this one has been coated on one side with a metal, such that when you shine light on it, there's a local demixing reaction in the water, and it can actually swim forward under its own power. It doesn't quite run and tumble. It actually gradually diffusively changes its direction of motion, but that doesn't really matter. So there's been a number of groups that have now created this artificial active matter. Now, why is this artificial active matter interesting? Well, if you look at a thermal assembly of particles, it'll just be a gas as long as you're at low enough density, and if you raise the density, you still have a gas as long as you're below 0.9 here. If you have these active particles at the same density, you can already see they're kind of a little bit clumpy. But if you raise the density high enough, there's a transition to where the active particles actually undergo phase segregation. There's a giant cluster where they're all crammed together, surrounded by a less dense active gas. This has been studied in some detail. It's really as a function of either the importance of their swimming, so how long they spend swimming in a correlated direction compared to the density of the active matter. You can really have a distinct transition between this sort of gas-like state and this phase-separated state. Why do they form this big cluster? Essentially, it's like a rate equation. They can crash into each other, but if there's just two, they'll probably go past. But if they're dense enough that there's a chance that three of them can crash into each other, they're very dumb. So they just keep trying to swim, and then nobody can go anywhere. And so until somebody decides to change its swimming direction, and then this can break apart. So there's a rate at which these little clusters can form, and if they're spending enough time swimming in one direction, or they're dense enough, these clusters form faster than they fall apart, and you can get the transition to the very large clustered state. All right, so we're going to take our same simulation that we did before, and so these are granular particles, and we're just going to add a motor so that they undergo run and tumbling. I'm going to skip that because I'm out of time here. So we see the same type of transition that people have seen, where you go from the gas-like state to this clustered state. And so now we take this and we put it in our pinning sites and ask, okay, what happens? We've essentially got this jamming transition if it's clean, where it all forms this one giant cluster. Can we get sort of a clogging state? So if you had a thermal particle and you were sending it through disorder, you would think, well, if I increase the temperature, it should be able to move more easily through here. So I could argue that having these particles swim is sort of like adding a temperature, and so I should be able to get them to go through more easily if I add the temperature. But actually we see kind of the opposite. As we increase the correlation time for their running, their ability to move through this quench disorder background is generally decreasing. So the more active they are, the harder time they're having getting through our background. But it's not monotonic. If you look closely, you'll see that actually there's a peak in the mobility. So initially they have an easier time getting through, and then as we make their correlation length longer, they have a harder time getting through. Well, what's happening is it's correlated with their ability to form these clusters. If they are at low correlation time, then they're able to, this is their velocity is increasing until this is a measure of how many particles are in a cluster. So then they start to form these clusters because they're bashing into each other and trying to swim into each other. Once the clustering starts to appear, the mobility drops. This is more easily seen with a movie. So this is in the case where we're essentially in the granular limit. We have the particles moving through a background here, and this is going to be the same background in all the movies. So you can see here they're basically clogged. They just can't get through this spot. Here they're able to get through, but they're having a little trouble. They have to sort of wait in order to get through, and here they're able to move relatively freely. So this is just has some local jamming occurring. If we increase their ability to run, the system really liquefies itself. It's quite dramatic. This is at the peak of the mobility. So here, this is the same disorder. This spot that was clogged, you can hardly even tell that it was an obstacle. And here, they're just essentially, instead of getting stuck, they back up and try again, and they're able to get through very easily. But you can have too much of a good thing if we let them run with a longer correlation time. Then what happens is every one of these obstacles can serve as a nucleation point for one of these clusters. And so then the particles spend so much time clustering that they forget that we're really wanting them to drift through the system, and so their mobility is going down. And so it's very likely that nature is aware of this phenomenon and is taking advantage of it. If it has bacteria that want to go through your soil or through you, that they probably are able to change their motility in order to do that efficiently. So essentially what we have for the active system is that when we're at this low activity, it's undergoing a clogging transition of the same type as what I showed you for the granular system. So this is kind of the granular limit. As we increase the activity, we get this actively induced flowing state. But if we increase it too much, we get an actively clogged state. And so what is the I'm making a distinction here between the clogging and the active clogging. But actually, if we look at the fluctuations of the motion in these two states, there's a very interesting difference, which is that, so this is as a function of obstacle density. This is for essentially the granular limit. The velocity is going to 0, and this is for the active limit, relatively long run length. If we look down here when the velocity is almost 0, so we're almost clogged, this is granularly clogged and this is actively clogged, the velocity fluctuations are really different for the two cases. So for the active clogging, we get very burst-like activity because they're forming these clusters, but then the clusters are breaking apart. It's extremely dynamic. For the granular limit, where they're hardly running, we get a much more uniform fluctuation. This is where it's trying to form the clogged state that I showed you at the beginning. And so if we do the distribution of the velocities here, we see a broad distribution of these burst sizes for the active system with an exponent close to 1.5. So we're really getting avalanche-like behavior from the active system, whereas the clogging system, it doesn't have that signature. So the activity is really inducing the avalanches here. And as far as I know, this is the first measurement of active avalanches that people have done. All right, so I think I have used up my time, but I have shown you, hopefully, that we have a distinction between this clogging and jamming behavior for granular particles, that the jamming behavior has signatures of a second-order equilibrium type phase transition with a diverging length scale, but the clogging behavior looks more like a non-equilibrium phase transition with this diverging time scale consistent with an absorbing phase transition. And then if you make the particles active, you can go between having a granular type clogged state at low activity to a flowing state at intermediate activity to an actively clogged state at high activity, and that actively clogged state is associated with this broad distribution of active avalanches. So thank you very much for your attention. This one or the raw data?
This one.
Uh-huh.
So the line that you drawn is where you're saying the jamming transition is.
Well, so it's a jamming transition here and it's a clogging transition here, which we.
So one class I missed this word. So the divergence is happening on either side.
Yes. Yes. So if you look at it, we see a diverging time scale on either side. This is the density where that line is occurring. And this is a lot of data kind of collapsed together. But if you're coming from either side, so if you're coming from here or coming from here, it takes longer. If you're in here, it takes a really long time for you to decide, is the system going to keep flowing or not? So, you know, and so it does start to depend on how long you've done your simulation. But so the shear jamming people have looked at in the absence of quench disorder. And so that's the big difference here, is that we've added quench disorder to the system. And so our claim is that rather than getting shear jamming, you actually wind up getting clogging. Now, if you're here where we're still kind of in the jammed regime, then you could say, well, maybe this is starting to be similar to shear jamming. But it's clear that this is not shear jamming. This is something else, because it's very dominated by the fact that you have the quench disorder. I left it out in the interest of time, but I have a diagram where we put some more axes on the phase diagram. One of them is quench disorder, and another one is activity.
So, if I want to do a 3D system, right, and if I want to look more local, not global, to distinguish between clogging and jamming,
Uh-huh.
what mesoscale parameter I should look at it to distinguish if this specific region, which is mesoscale bumpy particles, is it clogging or jamming?
So the two signatures that would, and again, you have to be a little careful because you could have an unclogged state somewhere that could come flow through and change things. But you could say, well, over this amount of time, I would call it jammed if the density is basically uniform, and if it's insensitive to which direction you are driving it. That would be something I would call a jam state. If it's a non-uniform density, and these usually go hand in hand, and it matters which way you drive it, that I would call a clogged state, so it's fragile. In other words, if you rotate the drive, it can flow, whereas in the jam state, no matter which way you try to drive it, it should be stuck.
Just density.
Huh?
Density.
So that would be, yes, well, like I said, so the local density should be homogeneous in the jam state, but heterogeneous and perhaps very strongly heterogeneous in the clog state. That's one of the signatures, even on a local scale. Ah, yeah. So the original simulation, it's very well defined in our model because we have a just a parabolic. We have just a spring interaction with some finite range. Well, there's a finite range of the force. So either they're interacting or they're not. Once they're out of the range of two disk radii, they don't interact with each other. So this is very well defined in the simulation. Exactly, it's just contact. Yeah. Well, I mean, when they're in contact, then there's a force. That's well, but then they go out of. So yes, I guess if they're just exactly touching, there would be no force. But the spring is quite stiff, so they tend to be these extremely tenuous contacts. There, we do see that a little bit actually at lower densities. There's a lower density movie I could show you where we get flickering because of this effect. But once we're close to the jamming transition, it's very well defined. They're either pushing or they're not touching. Yeah.
So last short question, Jérôme.
Could you apply this to human crowds, for example?
To human
Crows.
crowds. Oh yes. Well, so yeah, crowds are really interesting. The problem with crowds is that people are a little smarter than grains. But in
Marginally.
particular, I like to think about if you have panicked crowds, they enter what I call the granular limit, where I mean you're basically just these grains and you're clogging at the exits and so forth. So in the case of panic, I think that you can absolutely get these exact same physics. So of course you'd like to avoid that situation, but yeah, there's really interesting stuff with.
NASA has pictures of crowds of satellites, and they sometimes clog, jam, and form topological defects like vortices in Mars.
Oh yeah. Well, yeah. There's all. It's yeah. So I would. It's a fascinating subject, but it's like the bacteria. Yeah. So everyone, when you exit, be careful to not clog. You know.
Okay, thank you again.